In the video on ionization energy, we talked about adding enough energy to a neutral atom to pull an electron away, leaving behind a positively charged ion. So this represents ionization energy. And since it took energy to pull an electron away from that positively charged nucleus, right, we represented the ionization energy with a positive sign, right? Energy was put in, and our units were kilojoules per mole. So in the next video, in the next video, we're going to talk about adding an electron to a neutral atom. And for most atoms, adding an electron to a neutral atom gives off energy to form the negatively charged ion, the anion. And since this process usually gives off energy, right, we would represent that with a negative sign. And so this would be kilojoules per mole once again for the units. And this is one way to talk about electron affinity. So this represents electron affinity here. For some atoms, right, adding an electron does not give off energy. You have to actually put energy in to force that electron to form the anion here. And that's because the nucleus of some atoms, right, does not have an affinity for an electron. And so you have to add energy. And so if you were representing energy for a situation like this, right, it would take energy, so it should be a positive sign, right, so positive kilojoules per mole. And since this is pretty difficult to measure, most textbooks will either say the electron affinity for these atoms is greater than 0 or just equal to 0, and so that's what you see most commonly here. And so if energy is given off, as in this example, right, so if energy is given off, this electron that we're adding must have an attraction for this nucleus. And so that's how we're going to think about electron affinity. So in this video, we're just going to talk about 3 elements in period 2. So we're going to talk about lithium, beryllium, and boron, and we'll worry more about general trend in the next video here. So let's analyze lithium first. So we know that lithium has atomic number of 3, so there are 3 protons in the nucleus. And in a neutral atom, we know the number of electrons is equal to that number. So 3 electrons for lithium, 2 of them are in the 1s orbital. So here are our 2 electrons in the 1s orbital. And then we have 1 electron in the 2s orbital. So this is the electron in the 2s orbital. If we are adding an electron to lithium, that electron is going to go into the 2s orbital. And so I'm going to go ahead and add an electron to lithium in magenta here. And so this would no longer be 2s1, this would be 2s2. We now have 2 electrons in the 2s orbital. And this would no longer be the neutral lithium atom, this would be the lithium anion here, so lithium with a -1 charge. Let's analyze adding that electron to lithium in terms of the 3 factors we discussed in the last video, right? In the videos on ionization energy. We talked about nuclear charge, right? Because we know that the more positive the nucleus is, the more that positive charge is going to attract the negatively charged electron. So this electron in magenta is negatively charged. Opposite charges attract according to Coulomb's law. And so that +3 charge is going to pull that negatively charged electron in. So that's what we can think about, that attractive force between those oppositely charged, between those opposite charges there. So let's think about other factors, right? So we had electron shielding. So the idea of electron shielding was the inner orbital electrons or inner shell electrons, these electrons in the 1s orbital here, are going to repel this outer electron, right? They're going to shield it from the full effect of that +3 charge of the nucleus. Right? And these two concepts together, nuclear charge and electron shielding, give you the effective nuclear charge. And so the electron in magenta doesn't quite feel a full +3 charge due to the shielding effect of those inner shell electrons there. And then finally we talked about distance. Right, so the distance of the electron that we added in the 2s orbital from the nucleus, right? The closer that distance is, the more of an attractive force that electron is going to feel for the nucleus. And so when you add up all of those factors that we just discussed, it turns out that it's energetically favorable to add an electron to the neutral lithium atom, and 60 kilojoules per mole of energy are released when this happens. And so the attractive force of the nucleus, right, there is overall an attractive force of the nucleus for that electron, so lithium has an affinity for an electron, so it gives off energy when you add an electron. So that's the concept of electron affinity here. All right, let's do the same thing for the next element. So let's look at beryllium now. So we've moved on in terms of atomic number. We're now at atomic number 4, so 4 protons in our nucleus. right? Then we have 4 electrons, and 2 of those electrons go into the 1s orbital. So here are those 2 electrons in the 1s orbital. And then 2 of those electrons go into the 2s orbital. So here we have our 2 electrons in the 2s orbital. And these drawings are obviously not perfect. They're just very simplified to help us figure out these concepts here. So if we wanted to add an electron to the neutral beryllium atom, right, we couldn't add it to the 2s orbital. That 2s orbital is full. So we would have to open up a new subshell here. We would have to put that electron into a 2p orbital. So the electron configuration would be 2p1. So we would have to add an electron to the 2p subshell. So here's our electron in magenta being added to a 2p orbital. So this would no longer be the neutral beryllium, right? This would be beryllium with a negative charge like that. And so let's think about those 3 factors that we discussed, right? First, nuclear charge. That negatively charged electron is going to feel an attractive force from the nucleus, right? And we've increased the charge from lithium, right? It's now +4. So just thinking about nuclear charge alone, there's an increased attraction for that electron to the nucleus. However, we also have other effects to think about. So if we think about electron shielding, right, this electron in magenta is shielded by these inner shell electrons, right? So just like with lithium. However, with beryllium, right, we have these electrons in the 2s orbital, and since we added the electron in magenta to a 2p orbital, the electron in the 2p orbital is on average, right, further away from the nucleus. And so these electrons in the 2s orbital can do a little bit of electron shielding, right? They're a little bit closer to the nucleus on average, and so therefore they would shield that electron in magenta from the full effect of that +4 charge in the nucleus. And so there's a little bit more electron shielding than in the previous example with lithium. And so finally we think about distance, right? So distance, this electron in magenta is on average, right, further away from the nucleus than the example for lithium, the electron that we added for lithium. And so since it's further away, there's less of an attractive force for it. So even though there's increased nuclear charge, right, we have a little bit more electron shielding, and we have the electron that we're adding is a little bit further away from the nucleus. And so it turns out, when you look at the electron affinity values, it actually takes energy to add an electron to the neutral beryllium atom, and so the beryllium anion is unstable. And so one way of thinking about that is adding that electron to the 2p orbital, right, opening up a new subshell, means that electron is again further away from the nucleus, and so the nucleus must not have enough positive charge to attract that outer electron that we added. And so that's the reason for the fact that beryllium doesn't have an affinity for an electron here. So it would need to have an extra charge in order to effectively hold that electron. All right, and that's kind of what we see with boron here, right? So if we look at boron, right, we've now increased to atomic number of 5, so we have 5 positive charges in the nucleus. And when we look at the electron configuration for boron, right, 2 electrons in the 1s orbital, right, 2 electrons in the 2s orbital, and 1 electron in the 2p orbital. And this electron in the 2p orbital, even though this electron is on average further from the nucleus, right, we've increased the amount of positive charge in our nucleus. It's now +5, and so that extra positive charge is enough to hold that last electron. When we're talking about electron affinity, we're adding an electron to the neutral atom, and so if we added an electron to boron, right, this would no longer be 2p1, this would be 2p2. We'd be adding that electron to a 2p orbital. So I'm going to go ahead and draw that electron right here, like that. And so this would no longer be the neutral boron atom, this would be a boron with a negative charge. So once again, let's think about our factors. And so first we have nuclear charge, right? This electron that we added to magenta is going to feel an attractive force for the nucleus, right? And again, just thinking about the magnitude alone, the increased +5 charge means that electron would be attracted to it with a little bit greater force. If we think about electron shielding, right, so once again we have a similar situation to the previous example, right? We have some shielding from these 2 inner shell electrons, and since this electron we added is to the 2p orbital, right, that's a little bit on average further away from the electrons in the 2s orbital, so we're going to get a little bit of electron shielding effect from those electrons in the 2s orbital. And so we have a situation here where we have similar electron shielding but increased nuclear charge, and so the effective nuclear charge that electron in magenta fields is increased. All right. We also have distance to think about. All right, so this distance right here, all right, this is on average, right? The electron that we added magenta is going to be about the same distance as the electron magenta we added to beryllium, and so there's not much of a distance effect. And so because we have an increased effective nuclear charge for this situation, right, that electron magenta is going to feel more of an attractive force, and so boron has an increased electron affinity compared to beryllium, and we see that reflected in the value here. So negative 27 kilojoules per mole. So energy is actually released when you add an electron to the neutral boron atom. And so finally, let's compare lithium with boron, right? So both lithium and boron gave off energy when you add an electron to them, but we see that lithium actually gave off more energy. So lithium has a greater affinity for that electron, and we can explain that again in terms of where the electron is going. So for the neutral lithium atom, we add that electron to a 2s orbital. So let me go ahead and change color so you can see that. So we add that electron to the 2s orbital here. So here's the electron that we added. For boron, we add that electron to a 2p orbital. So this electron right here. Since the electron we added to the 2s orbital for lithium, so back to this one again over here on the left, that electron has a little bit less electron shielding, right, and it's closer to the nucleus. And so since it's not as shielded and it's closer to the nucleus, it has more of an attraction for that positively charged nucleus. And so that's just one way to explain the slight difference in energy here, why lithium actually has a higher affinity for an electron than boron does. In the next video, we'll cover the rest of the elements here on the second period. So we'll talk about carbon, nitrogen, oxygen, fluorine, and neon.